Alright, good afternoon or good morning class, whichever classes you're listening to this in. Our next section is on probability. So we're looking at just basic probabilities here. There's three types we're going to look at today: experimental probability, theoretical probability, and geometric probability. So the first one you're going to see here is an experimental probability. It's the probability that an event occurs within the constraints of some sort of experiment or some sort of scenario. For these probabilities, if you look right here, what we want to set up is the number of successful outcomes over the total number of trials. With probability, you always want to make sure you're putting the total on the bottom. So what I had done here in the past is I had run a simulation with this die where I rolled it, and I had tallied up how many times we got each number. Typically, if you were looking at the probability of getting a number, you would say you have a 1 in 6 chance, but because this is an experiment, we look at how many times it occurred in the experiment. So this first one here, this means the probability of getting a 4. And the probability of getting a 4 was 3 out of, we would need to know the total number of times we rolled the die here, so we count this up. That's 3, 7, 8, 9, 10, 11, 12, 13, 14, 15. I ran that 15 times. And we reduce that, that's 1/5. Or if it asked for a percent, that was 20%. And then the probability of getting a 6, we only rolled 1 6 out of 15. So that's 1 out of 15, or 6.7%. And I'll try and be clear about which one I want, if I want a fraction or if I want a percent. Here's a couple more theoretical probabilities. These are just word problems. So we have a scenario here: a baseball player hits the ball 22 times out of 50. What is the probability he will hit the next ball? So with this, we're just going based off the information we know currently. We're not going to actually think about what the next scenario would be. So our current probability that he's going to hit a ball is he's hit it 22 times, that's the number of successes, over the total number is 50. That I think I'll give as a percent here. That's going to be a 44% chance. And part B asks the opposite. What is the probability that he will miss it? You have one of two options here. The first option is to take our last percent, since this is the opposite side of it. We know that they need to add to 100, so you could just do 100 minus 44, which gives you 56%. Or your second option is to figure out how many times he missed it. He missed it, if we do 50 minus 22, he missed it 28 times. So you could do 28 out of 50, which is still 56%. Our second example of experimental probability here is with flipping a coin, heads versus tails. Out, if we just did the actual probability, it would be a 50% chance, but now we've done this experiment and it's come up heads 24 times. Out of, that's our number of successes, out of, the bottom needs to be the total. So you need to make sure you add the 24 plus the 16 to get the total. That's what number has to go on the bottom, that's 40. So that's 24 out of 40, which is 60%. So a little bit higher because you got heads more often than you got tails. This is just the setup for theoretical probability now. For theoretical probability, it's the probability that an event occurs when all outcomes are equally likely. So in order for you to set up a proper theoretical probability problem, everything has to have a likely occurrence. There can't be something that's weighted or anything like that. So the probability of the event is the number of successful outcomes, again, over the total number of outcomes. So it's successes over total. The other definition I have for you here is sample space. The sample space is the list of all the possible outcomes, and we're going to see that in the next example. Alright, so now we're going to do a probability with what they call a number cube. When you see that in your directions, that's just another name for a 6-sided die. The first thing we want to do is write out the sample space. So the sample space for a 6-sided die would be 1, 2, 3, 4, 5, 6. Those are all the possible outcomes from a 6-sided die. So we're just going to look at these different probabilities next. We want to know the probability of getting an even number. Even numbers would be 2, 4, and 6. So that's 3 of the numbers out of the total is 6, which is a 1/2 chance. Part B asks for the probability of getting a number 2. There's only one number that's 2. Be careful there, you don't want to actually put the 2 on top. That's 1 out of 6 chance. Probability of getting a prime. I give you a note over here on the side. Prime numbers are numbers that whose only factors are 1 in itself, but 1 does not count as a prime number. So that would be like 2, 3, 5, 7, 11, so on and so forth. So the prime numbers up there are 2, 3, and 5. 1 does not count as being prime, so don't count that. So that's 3 out of 6, which is 1/2. And then probability of being a multiple of 3, which means you can divide it by 3, that's 3 and 6, so that's 2 out of 6, which is 1/3. We have one more theoretical probability here, and that's just dealing with a bag of something. You could do a bag of marbles, you can do a bag of lots of different things, but this is going to be a bag of candy. So there are 4 Twix, 5 Snickers, 8 M&Ms, and 3 Starbursts, and we want to know the probability of getting a Twix. So the top number obviously is going to be 4, because that's how many Twix there are. Remember, to get the bottom number, you got to get the total, so we have to add the 4 plus the 5 plus the 8 plus the 3. That should come out to 20 things of candy total, so that's 4 out of 20, which is 1/5. Then we want to know the probability of not getting an M&M. So that would be, the total is 20 minus 8 of them are M&M, 12 of them are not M&M. So that's 12 out of 20, which reduces to 3 out of 5. And then the last probability we want to know is Snickers or Starburst. So we know there are 5 Snickers and 3 Starbursts, and we can add those together to get a total of 8 out of 20, which reduces to not 4 out of 5. Make sure you reduce correctly, 2 out of 5. So there's your probabilities. The last type of probability we're looking at is geometric probability. To get the geometric probability of landing in some space, you have to take the area of the chosen space over the area of the total region. So we want to know, this is like a bag board. We want to know the probability that when you throw the bag's going to land in the hole. So we would have to know the area. I'm going to set this up first. The area of the circle is where we want it to be. Over the area of the total region would be the area of the rectangle. So when you do geometric probability, it's all about finding the area of the shapes that you see. So now we need the circle formula. Circle formula is pi r squared. So for the top, we're going to do pi times the radius is 1 squared. That's 1 pi, or 3.14. The rectangle, so this is a circle, the rectangle is going to have an area of length times width, which is 6 times 3, which is 18. So then your probability is to take the area of the circle divided by the area of the rectangle. And then we're going to do these as a percent, so we're going to multiply that by 100. And you should get 17.4%. And that's all about the basics of probability. Hopefully you find this pretty clear and you're able to complete your homework, and I hope to see you all on Tuesday.